This streamline pattern closely coincides with the predictions of potential theory. As early as 1904, Prandtl recognized that this theory could predict pressure distributions when the viscous boundary layer is thin and does not separate. No matter how thin the boundary layer may be, however, it has important effects. Skin friction drag is an example. In the laminar boundary layer, fluid mixing and viscous skin friction are low, but laminar layers are frequently unstable and result in turbulent flows, which involve much more rapid mixing, producing higher skin friction drag. Another example of the importance of the boundary layer is its ability to totally disrupt the main flow. The retarding and eventual reversal of the flow next to the surface of this wing in a region of adverse pressure gradient causes the entire flow to separate. The presence of the boundary layer produces many design problems. To help overcome some of these, methods have been developed for controlling the boundary layer for the fields of aeronautics, for ships, submarines, for fluid machinery, and for propulsion. The most intensive effort has been directed towards increasing the lift and decreasing the drag of wings. To illustrate the ideas of boundary layer control, we'll examine some of these techniques. The two things that we want to control are transition and separation. We'll look first at this one, the factors affecting the transition. One of the ways of reducing the skin friction drag is to maintain as much of the boundary layer as possible in the laminar state. Transition to turbulence occurs because the laminar boundary layer becomes unstable to some type of disturbance. Here is transition slowed by a high-speed camera. Unstable waves in the laminar flow amplify to form discrete eddies. These, in turn, produce the highly disorderly motion of turbulent flow. The location at which transition occurs depends both upon the nature of the disturbances to the laminar boundary layer and its stability. The designer has learned to control some of these factors. Disturbances arising from rough surfaces can be reduced. Other disturbances, such as noise, vibration, or airstream turbulence, can sometimes be avoided or isolated. Designers have also learned to use the strong influence of the pressure gradient on the stability of the laminar boundary layer. That is, its ability to damp out disturbances. This can best be demonstrated by use of a pressure distribution tunnel. Combinations of favorable and unfavorable gradients occur over the surfaces of aerodynamic shapes. This airfoil has a maximum thickness of 12% of the chord length, located about 1/4 of a chord length aft the leading edge. The model contains pressure tubes mounted flush with the surface for the measurement of the static pressure distribution. These tubes are connected to the manometer alternately from the top and bottom surfaces. When the profile is set at 0 angle of attack, the pressure distribution produces this picture on the manometer. The pressure is highest at the stagnation point on the leading edge, but decreases as the air flows aft until a minimum is reached near the point of maximum thickness. After this point, the pressure increases so that an adverse gradient exists up to the trailing edge. The profile is symmetrical, so that at 0 angle of attack, the pressure distribution over both surfaces is of equal magnitude. Increasing the angle of attack destroys the symmetry of the distribution. The minimum pressure point becomes more pronounced and moves forward, increasing the severity of the adverse gradient. This is an identical profile in the smoke tunnel. The flow tends to remain laminar up to the minimum pressure point. As the angle is increased, the minimum pressure point moves forward. The extent of the laminar boundary layer is steadily decreased until at the higher angles it exists only in the region of the leading edge. At negative angles, the upper surface gradient is favorable over most of the surface. As we can see in the smoke tunnel, the boundary layer remains laminar almost to the trailing edge. For a given lift, we get a greater length of laminar flow by modifying the pressure distribution through a change in the airfoil shape. To demonstrate this, the lift of this profile at this angle of attack will be indicated by the area of this pattern drawn on the manometer. Here is another airfoil, adjusted to give the same lift. It has the same maximum thickness as the previous one, but further aft, close to the mid-chord point. As a result, at low angles of attack, the extent of the favorable pressure gradient over the upper surface is increased well beyond that of the previous case. As the angle of attack is increased, the situation changes radically. Because of the geometry of the profile, the radius of the leading edge is small. As the forward stagnation point moves downward, the flow passing over the leading edge must accelerate rapidly, producing this abrupt pressure minimum and strong adverse gradients. At the low angles of attack, the boundary layer remains in a laminar state for an appreciably greater distance than with the previous profile. But as the angle is increased, the transition point abruptly moves forward, covering the surface with turbulent flow. Turbulent boundary layers thicken more rapidly and produce greater skin friction than laminar ones. Thus, reducing the extent of turbulent flow reduces the drag of the profile. We can verify this by measuring the loss of momentum in the wake of the airfoil, using an array of total head tubes. The tubes are located far enough behind the profile so that the static pressure in the wake is nearly the same as that in the main flow field. The loss in total head reflects a change in streamwise momentum flux and is a measure of the profile drag. The airfoil under test is the one with its maximum thickness at the quarter chord point. The defect in total head in the wake shows up as this pattern, which we'll mark for future reference. When the laminar flow section is mounted in the tunnel at an angle of attack producing the same lift coefficient, the resulting momentum defect is markedly smaller. Using geometry to provide favorable pressure gradients is an example of this method of controlling the nature of the boundary layer. But as we've seen, adverse gradients can never be completely avoided, and under certain circumstances can actually become more severe than on conventionally shaped bodies. A rather different means of stabilizing the laminar boundary layer is the use of suction. Suction may be applied either through porous surfaces or through finite slots, such as these. In this model, the arrows indicate which slots are open, but suction has not yet been applied. Now suction is turned on. Now off. Suction reduces the thickness of the boundary layer by removing the low momentum layers next to the surface. A more stable layer results, and transition to turbulence is delayed. Ideally, to achieve stabilization of the boundary layer at various angles of attack, an infinite number of slots or holes provided with an infinite number of suction variations would be required. Since this is somewhat difficult to achieve in practice, compromises must be made as to the number of slots and their location, as well as to the amount and distribution of suction. The slot arrangement in this profile is such a compromise. Again, using an array of total head tubes, we see that without suction, the wake is broad. Applying suction reduces the streamwise momentum loss in the wake. The wake reduction is not symmetrical, since suction is applied only to the upper surface. Power is needed to achieve this drag reduction. The optimum condition occurs when the total drag, the aerodynamic plus suction power converted to an equivalent drag, is a minimum. There are many cases when it's control of the separation of either a laminar or turbulent boundary layer that is of importance. Suction can be used for this purpose as well. This profile is at a moderate angle of attack. The transition point is well forward, and a large portion of the upper surface is covered with turbulent flow. Now we apply suction through the slots on the upper surface. The laminar boundary layer is restored at this angle of attack. However, with increasing angles, suction is unable to maintain the entire boundary layer in the laminar state. Increasing the quantity of suction helps somewhat, but since this means more suction power, and hence more equivalent drag, the point of diminishing returns is rapidly reached. Even though we can't maintain a laminar boundary layer at these higher angles, suction exerts a profound effect upon the turbulent layer. If we turn it off, the flow separates immediately. Applying suction reattaches it, although this is not always the case. In general, it will require less suction to maintain an attached flow than to overcome separation. We can watch reattachment in this slow motion scene. When the flow is separated, suction draws air into the slot from the entire separated region. Reattachment may be obtained either by the gradual extension of attached flow or by literally sucking away the separated area. The extension of attached flow can readily be achieved if sufficient suction can be applied upstream of the separation point. But if suction takes place entirely within the separated area, the suction quantity required for reattachment may be excessive. The flow over this profile is completely separated, as shown by the violent action and upstream direction of the tufts. Suction reattaches the flow. This is also reflected in the pressure distribution. When stalled, this profile suffers a loss of lift. As suction is applied, lift is restored. As the flow is reattached, the pressure distribution approaches that of an inviscid flow. The irregularities in this pattern occur where the pressure taps are located near the suction slots. In the case of suction, separation control is accomplished by drawing the low momentum layers from the bottom of the boundary layer into the suction slot. This draws the higher energy air from the outer layers closer to the surface. Depending upon the circumstances, this same action can be accomplished by these other techniques. As an example of adjusting the pressure field, here is a laminar separation at the leading edge of a thin profile. Separations like this can frequently be avoided by a change of geometry, such as the deflection of a nose flap. Mixing of the outer flow with that next to the surface can be achieved through the use of turbulence or vortex generators. In many cases, such mixing is sufficient to suppress separation of the turbulent boundary layer if the adverse gradients to be overcome are not too severe. Blowing jets directed into critical areas are also useful. Frequently, these can be created by utilizing the pressure difference that exists on the aerodynamic bodies themselves. The leading edge slat leads air from a region close to the stagnation point through a converging channel and ejects it at high speed at a point of low pressure on the upper surface. This same concept can be used to decrease the extent of separation on a deflected high lift flap. Air can be led from the high pressure region below the flap through a converging channel and ejected over the upper surface close to the point of minimum pressure. This helps to overcome the strong adverse pressure gradients existing on the upper surface of the flap. Multiple slot arrangements, though more complicated, have proven to be particularly effective. Still greater effectiveness can be obtained from blowing jets if they are produced by the direct application of power rather than by the limited differentials available on the body itself. The jet, moving at high speed through the surrounding fluid, creates regions of high viscous stress at its edges, and as a consequence, drags substantial amounts of fluid along with it. When such a high-speed jet is near a curved surface, the interaction of the boundary layer with the jet causes it to bend and to adhere to the surface. This is called the Coanda effect. Here it is used to conduct the jet momentum to a region where separation is most likely to occur. Air can be blown from the fixed portion of a profile to increase lift by preventing flap separation. Flap separation can also be overcome by suction. If a quantity of air, much more than required for laminar boundary layer stabilization, is drawn through a slot just ahead of the flap, the boundary layer is thinned so that the outer flow is drawn down to the surface of the flap, serving to retard the onset of separation. If more suction or blowing is supplied than that necessary to prevent separation of the flow over a deflected flap, rather more lift is measured than would be expected. In the case of suction, the low pressure at the slot inlet acts like a concentrated sink, altering the potential flow to increase the lift. A blowing jet contributes to the lift in several ways. It overcomes separation. It produces momentum that can be directed to add to the lift. And experiments show that there's yet another increment of lift, that arising from the so-called jet flap effect. When a jet is blown from the trailing edge in the streamwise direction, the magnitude of the viscous shear along its boundaries is so great that the jet's effect upon the free stream resembles that of a line of distributed sinks. When the jet is rotated and issues into the free stream at an angle, it is gradually turned, the rate of curvature depending upon the relative velocities and the fluid momentum. Each element of the jet sheet is subjected to a centrifugal force, which is in turn just balanced by pressure forces. The curved sheet thus supports a pressure difference, much as if it was a solid flap. This is reflected on the profile as a change in circulation. When the jet is directed downward, the lift is increased. When it's directed upwards, the lift is decreased. The jet flap and the sink effect primarily influence the potential flow field. They are sometimes referred to as circulation controls. Frequently, however, they are grouped under the general heading of boundary layer control. So far, we have seen various types of control systems. In applying them, many practical factors must be considered. Typical of these is the possibility of inducing a second separation while attempting to control the first one. Both the leading edge and the trailing edge flap of this thin profile are deflected. Because of severe pressure gradients, the flow is separating from the lower surface of the leading edge, from the break of the leading edge flap, and from the break of the trailing edge flap. By blowing air over the trailing edge flap, the separation in this region is suppressed and circulation of the profile increased. This increase in circulation so alters the flow field that the adverse gradient at the leading edge vanishes, and separation at that point is also suppressed. Separation at the leading edge flap break still exists because of the small radius of curvature at this point. To approach the potential flow pattern, it is necessary to overcome this separation by diverting some of the air now being blown over the trailing edge and to blow it over the leading edge flap break. Although this film has been concerned only with aeronautical applications, similar techniques can be readily applied to diffusers, bodies of revolution, or fluid machinery. Boundary layer control may, in fact, be applied wherever the transition or separation of the boundary layer affects performance.